Let's start chapter 4. First section is the area under a curve, and there is distance, but we mainly focus on area under the curve. Okay, this section is kind of a bit messy, requires perfect calculation. So if you're using calculator, be sure that you're using accurate decimal numbers. So what is the idea? Let's say you're given a function f, and they ask you to calculate area under a curve. That means the area between the curve and the x-axis. So let's assume the curve is above the x-axis. So we're looking for this shaded area. If this function f was a constant function, something like that, straight line, assume this is a straight line, and they ask you to calculate the area, then you'll get a rectangle. You should be able to calculate this area. If it was like a half circle, since you already know the area for a circle, radius pi r squared, then since it's half of it, you divide by 2. So for these cases, you should be able to calculate the area without any necessary requirement. If it was a straight line, then you can break it into a triangle, calculate the area in over a specific interval. So here, what we talk about in this section is mostly an approximation, because if you have a curve that you cannot use any geometric representation for, the ones that we know of, circle, triangles, squares, rectangles, and stuff like that, what you can do is you try to approximate. What does it mean? Let's say you want to calculate the area under this curve f. What we can do is, let's approximate this area by a rectangle, some rectangle, something like this. And we want to calculate from A to B. So we approximate it with this rectangle and say, okay, now this rectangle is not exactly accurate for the area, but it's a good approximation. You can choose the height of the rectangle based on where you see it's most fit. So these two areas probably are going to be close in terms. So if you're adding something here and taking off some other part, then the area will kind of be close to the exact value. So instead of doing that, what we can do is these approximations can be broken down the other way. That means first you start with one rectangle. Say I approximate this area by this rectangle. Then you say, okay, this is not a good approximation. How about if I break this into two rectangles? Left side, I will do this approximation, and on the right side, I'll draw this rectangle. And this is kind of a new approximation for the area under the curve. And if it's not good enough, we will try to break this into more pieces. Let me go back, and this, maybe I will make it into 4 rectangles. So I'll break this into 4 pieces, and then I'll approximate. Here is an approximation, here is an approximation, and another one, and maybe here. So now you notice that the more rectangles that you use, the better the approximation becomes. And the question is basically, how do you choose the height of these rectangles? So the height of each rectangle, so this height here, we've chosen, it's kind of random because we don't know how specifically you can pick. Which points do you pick on the graph? Do I pick this point to approximate the graph with, the height of the rectangle with, or do I pick this one? Sometimes you're given a point and say use these points. Those are called the sample points. So there are certain selection of these sample points that we choose. One is, the very easy one is using the left or right endpoints. So let's say we've broken down this A to B into 4 pieces, and they ask you use the left sample point. So in this section, so in this first rectangle, what I'm going to do is I'm going to look at these two ends of the graph, so on these two endpoints, And I'm going to choose the left point as an approximation. So I'll approximate this graph, this area with this rectangle. So if they say use left endpoint, in each subinterval, so this is a subinterval, in each subinterval, I will use the left endpoint as an height to approximate the function. In the next one, I'll use the left endpoint again. Here's an approximation. In the next one, I'll use the left one. And in the next one, I'll use the left point. So in each interval, I've used the left endpoint. What if they say use the right endpoint? So these lines, you have to ignore these endpoints. So in each interval, use the right endpoint. So I'll use this right endpoint to approximate. This would be a rectangle that I will use to approximate this area of it. And here I'll use that right endpoint. I'll use this right endpoint. It may not match the left endpoint. Probably most of the time it doesn't. Here I'll use the right endpoint. Sometimes the right endpoint is not a good approximation. Sorry about that. So what they tell you is, instead of using the right endpoint, maybe choosing the middle point would be a better sampling for the height. So instead of choosing left or right, we can pick the middle point as a sample. So this would be a height. So this middle point means in the interval you're given, pick the middle point and use that as the height of the rectangle. So the y value of that middle point on the curve will give you the height of the rectangle. Here I'll pick this middle point and approximate the area under the curve with this y value of that middle point. Here I'll pick that one. And you notice sometimes the middle point is a better approximation. Sometimes it's not going to be the better approximation. If the curve is something like that and you pick the middle point, you're overestimating the graph. If you pick the left point, you're underestimating. If you pick the right point, you're underestimating. So what you do is, normally, depending on the question, depending on the curve, you choose the sampling yourself, and depending on how accurate you want it, you pick the number of subintervals that you want to divide the graph into. And there is another case that they say use the lower and upper sum. Lower and upper sum means if you look at each interval, let me erase this picture so we can start again. This actually should have been easier. I selected and delete. So here, let's say you want to calculate the lower and upper sum. Let's say you're given this curve. This is a graph for the function f. And let me change it a bit so you have increasing and decreasing part so you notice the difference. Okay, let's say you have it from A to B and you want to approximate the area under this curve using the lower values. What does it mean? That means if you divide this into 3, 4, as many pieces as they tell you, n pieces. In this case, let's divide it into 3 pieces. It means the interval A to B has been divided into 3 pieces. In each interval, pick the smallest y value possible. That means pick the minimum height to approximate the area. So I will pick this point here. I'll pick that point. In the next interval, the smallest value happens to be here. So this is an underestimation of the graph, and this is the smallest possible summation of the areas. Any other point that I pick, if I would have picked this point, it would be a bigger rectangle, so therefore a higher area. So this is called the lower sum of the areas. And in the other sense, you can pick the upper sum by picking the highest values. So here in this interval, the first interval, I can pick this endpoint and estimate this area with this rectangle, and then overestimating the area. In this one, I can pick this point, estimate the area here by picking the highest y value. Similarly, in the next one, I can pick that point and say, now that is an overestimation of the graph. So all these are choices to approximate an area. It's not an accurate data, it's an approximation of the area. Okay, later on we will discuss how to find the exact value for the area under a curve. So these are all just built in. So here's a notation you should notice. Sometimes they use L, N, and Rn for the right and left endpoint. For lower and upper sum, they use L and U. So depending on the textbooks, they have different notation. So make sure that you understand what the question says. Sometimes they use MN for the midpoint. In your homeworks, if they use L and R, that means left and right endpoints. Midpoint, normally they will mention it. And what does N mean? It means the number of intervals that you want, subintervals that you want to divide in. So if they write L3, it means divide the interval into 3 pieces. So N is the number of some subintervals, number of subintervals. Okay, and there's a delta X notation. What does delta X represent? Is the length of each subinterval. That means basically this length in each subinterval. And normally we'll divide it into equal pieces. My dividing in this sample, in this graph, is not accurate. So the lengths of each subinterval are equal, and it's not a specific thing, but we pick it to be equal. It's easier this way. And so here delta X represents that. And how do you calculate delta X? It's basically the total length, which is B minus A, divided by number of stencils that you want to have. So if you want to have 3 subintervals, you'll divide it by 3. If you want to have n of them, you'll divide by n. So delta X is simply B minus A divided by n. Yeah, so we already know the lengths of for each of these rectangles. We already know this length. This length is given as delta X. The question becomes, how do you pick this height? As we discussed it, you could use these sample points, either left point or right point or the middle point. Or you can use the lower and upper sum by picking the points to be the lowest value or highest value. Okay, so how do we approximate an area? The area of a region S that lies under a graph F would be approximated by, so here Rn in this case is called the Riemann sum. So the Riemann here in this case means use the sample points x1, x2 up to xn. So in each, so here draw a graph, and let's say this is been divided into n pieces. From A to B has been divided into n pieces. This length simply delta X. Okay, let's say you pick this point. You pick this point. Okay, this point, the first sample point, I'm going to call it x1. What is the height of the rectangle? It is basically the function evaluated at that point. That's the height of the rectangle. It's the corresponding y value. How about the next point? What is the height of the rectangle? It's the corresponding y value at this next point. So the next point, we call it x2. So it would be f at x2. So in each rectangle, you have the height, you have the length. So length and width multiply by each other, they will give you the area. So it would be delta x times f of x1. That would be the area of the first rectangle. Delta x times f of x2. That would be the area of the second rectangle. So if I add all those up, what do I get is an approximation for the area under the curve. So here's this notation, means area, first area, second area, third area, and so on up to the nth area. Add all those up. And the more we pick we let the n to be larger, that means the more number of rectangles that we have, the better our approximation becomes. So it means if you let n approach to infinity, you almost get exactly the areas you want. So your approximation would be very accurate by choosing n to be very large. This is just a definition. So here's an example. I only do one example because it's too many calculation. So here, let's look at this function x squared minus x and given over interval 1 to 3. You don't need to graph the function, but it's just to make sense more. Here is 1, is 3, and you're given x squared minus x. So x squared minus x equal to 1 is, if you replace 1, you get 0. If you replace 3, what we have is 3 squared minus 3 is 6. We have 6. Okay. So the curve is a parabola, so it kind of looks like this. This is a function f. Okay. Let's answer part A. Using right endpoints, when n equals to 4, approximate the area under the curve. So n is given 4. So here's part A. N is given 4, and you want to use the right endpoint. So what would be the area? Area would be, first find out delta x. Delta x would be the length of the interval divided by number of stencils that we want to have. 3 minus 1, 3 minus 8 divided by 4. It would be 1/2. That means from this point, if you start and go 1/2, you'll get 1 plus 1/2, it will be 3/2. If you go another 1/2, you'll get 2. If you go another 1/2, you'll get 5/2. So if you divide this interval accurately into 4 pieces, here these lengths, each one must be 1/2. Each of these lengths must be 1/2. That's what we found at this point by finding delta x. And we have 4 stencils. And now what you want to find out is the height for each rectangle. Since they say use the right endpoint, so in the first subinterval, I'm going to use the right endpoint. The right endpoint means using this point to approximate the height. So what am I approximating is this area as to be the area under the curve. You will notice that this is an overestimate. If you look at the next one, we'll use the right endpoint again. Here's an overestimate. Here, right endpoint, again overestimate. Since the graph turns out to be increasing, by picking the right endpoint, it's always overestimation. But we don't really care since they ask specifically for the right endpoint. So what would be the approximation of the area? It would be, there is no limit necessary. So you say it would be the length times width in each one. So it would be, 1/2 times f at the right endpoint. F at the right endpoint was 3/2. Plus 1/2 times the next interval, 2. Plus 1/2 times f at the next interval was 5/2. And 1/2 f at 3. So if you calculate each one of these numbers, you'll get 1/2 times f of 3/2 would be 3/2 to the power 2 minus 3/2. This is the problem with this question. You should calculate all these numbers. It would be 3/2 squared. Show you what is 3/2 squared is 9/4 minus 3/2 plus 1/2 times f of 2 would be 2 squared 4 minus 2, so it would be simply 2 plus 1/2 times f of 5/2 would be 25/4 minus 5/2, and plus f of 3 is 6. We already knew that one. Okay, so if you add all these numbers up, you'll get an approximation. So I'm gonna try to do as fast as I can. 9/4 and 25/4. That is 20/34 divided by 4. That's 17/2. 17/2 minus 8/2. 8/2 is 4, so here you will have 2 plus 6, so 4. 17/2 plus 4. I skipped some steps, try to calculate this fast than I can. What is that? 8/2 plus 17/2. 8 and 17 is 25, so you get 25 over 4, which is almost, sorry, not 12 and a half. It is 6.25. This is the problem with these type of questions, is you have to go through these calculations. That's the problem. Otherwise, it's not difficult. It's just messy, and make sure that you do not make a mistake. If I've made a mistake somewhere in this calculation, please write the correct answer in the comments so everybody noticed that I've made mistakes and they figure out the correct answer. Using the midpoint. So how about part B? Part B would be using the midpoint. Right in the next page. Using midpoint when n equals 2. So B, midpoint, and when n equals to 2. So let me draw this graph again. Again, it's not required, but I'm going to draw it so it's easier to see what it means. This right there is dot. Okay, so it says break this interval into 2 pieces. This is easy. This middle point must be 2. Okay, you can calculate delta x. You can see the delta x is the difference. It's this length basically, which is 1. But if you calculate, it's 3 minus 1 divided by 2, which is simply 1. You'll get exactly this one. So we have the length as 1. How about the height? It says use the middle point. So it means use this midpoint to approximate. But it's not the midpoint of the curve. It's midpoint here. It's between 1 and 2. You will pick the midpoint. What is that midpoint? It's 3/2. Between 2 and 3, the midpoint is 5/2. And we will use this to approximate. So this would be the rectangle to approximate the area there, and here's the rectangle to approximate. You will notice that this is kind of closer to the accurate, since you will have an overestimate and underestimate. They will kind of cancel out each other. So what is delta x? It's simply 1. So what we need to find out is 1 times f at the midpoint is 3/2, corresponding y value, plus 1 times f at the other midpoint is 5/2. And since we had 2 intervals to approximate, this is it. F of 3/2, we already figured that one out. It was, let me write it underneath, it equals, I'm going to ignore the 1 dot, because that doesn't change anything. You'll have 9/4 minus 3/2. That was the f of 3/2, plus f of 5/2 was 25 over 4 minus 5/2. And what we get is 34 over 4, again 17 over 2 minus 8 over 2. 17 over 2 minus 8 over 2 is 9/2. And this is 4.5. So in the last part, you notice that we got 6.25 as an estimation. Here we have 4.5. So this last one, we already knew that we were overestimating because we had these extra pieces. So 6.25 was definitely more than what we were, what the area is. And here we have 4.5. We expect it to be closer to reality because these two sections kind of cancel out each other. It may not be exactly 4.5 because this area seems to be larger than the other one that we're canceling out, but it's closer. The more points that you pick, the better the approximation becomes. The more stencils you pick, the better the approximation. Yeah, using sample points, part C, using sample points given 1.1, 1.8, 2.5 when n equals to 3. So here in this case, you're given the sample points. Specifically, you say, here's 1, here's 3, here's the curve, 6. And they say, use these sample points, part C. They use 1.1. First, they say divide this into 3 pieces. That's first. And you can figure out what these specific points are by adding the lengths of each interval. The points are 1.1, 1.8, and 2.5. 1.1, 1.8, maybe somewhere here, and 2.5. Okay, so each sample point should be in the next interval. You should have one sample point in each interval. So here they say use that point to approximate the area. Use this point, 1.8, to approximate the area. And here you use 2.5. Here's the y value of 2.5. Approximate the area by using 2. So what it means is first figure out delta x. What is delta x? It's b minus a, 3 minus 1, divide by the number of stencils, 3 of. So we'll have 2/3. So that means if this is 1, the next one should be this point here, end of this interval. Make sure everybody knows what we're talking about. Length of this, the end of this interval should be 2/3 apart from 1. So it should be 1 plus 2/3. The next one here should be 1 plus 2/3 plus another 2/3, because it should be 2/3 apart from the one before. So 1 plus 2/3 plus another 2/3. So you can simplify these numbers and you can find out the exact location. So this one is 5/3, and here you have 7/3. And 3 minus 7/3 is exactly 2/3. So we've divided this interval into 3 equal pieces. So how do you find the area? The area must be 2/3 times f of 1.1 plus 2/3 times f of 1.8 plus 2/3 times f of 2.5. These are decimal values. I'm gonna leave it for you guys to add it up and find the area. And later on we'll discuss that you can exactly find this area as an accurate number. These are approximations, but we can find this exact number later on in section 3 or 4. I think section 3. And we will discuss how to find it as we go along. So at the moment I'm going to stop at this point. This is the first section of chapter 4.